When your vector dB gets big, fast quietly becomes slow. We'll use partitions and scalar filters in Milvus to keep P95 latency under control. You notice occasional slow queries as data grows. One query spikes while most stay quick. That unpredictability kills user experience. Today, you will learn how to route queries to smaller subsets and apply a cheap scalar cutoff so searches scan far fewer candidates and keep latency steady. I'm Professor Pi, teaching search and IR from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. Think about a store with many aisles. Searching every aisle for a single item is wasteful. Partitions let you restrict the search to one aisle. A scalar filter is like saying, show me items under a price. Together, they shrink the work per query. Success looks like the same query cost regardless of collection size, and P95 latency that does not drift upward as you add millions of vectors. At a high level, partitions are logical buckets inside one collection. They let you group similar vectors or group by metadata. Scalar filters use a simple numerical or categorical field to prune candidates before heavy distance math runs. The idea is to avoid computing distances for vectors that fail a cheap test. A small example is two partitions, A and B, each with a few 2D embeddings and a price field. If you only search partition A and require price less than 2.5, you read far fewer vectors. We will build a tiny Milvus demo that does exactly that. It connects to Milvus, creates a compact collection with an auto ID primary key, adds partitions, inserts two-dimensional vectors with a price scalar, and then compares an unconstrained search to a partitioned, filtered search. That prepares you to scale this pattern to larger systems. Now we verify the server connection. This snippet connects to Milvus and verifies the server is reachable. It uses the pymilvus connections connect call to open a local client session, and then calls utility getServerVersion to confirm the server responds. The variable alive is true when a non-empty version string is returned, which is a quick health check without any collection work. Keeping this check lightweight helps catch connectivity issues early, before schema or data steps. A stable connection ensures all following partition and filtering operations can run predictably. The printed result confirms that Milvus is up and ready for search tasks. Next, we define a minimal schema and create the collection. This snippet creates a compact Milvus collection ready for partitioned inserts. We define three fields with pymilvus. PK is an auto-increment primary key. P is a float scalar used for filtering. And V is a 2D embedding for similarity search. CollectionSchema bundles these field schema definitions, and collection creates the table named tpart. Keeping the schema minimal reduces overhead and makes examples easy to follow while focusing on partitions and filters. Auto IDs mean we don't supply primary keys during inserts, which keeps later code short. The printed result confirms the collection exists and matches the intended name. Now we create partitions and insert sample points. This snippet creates partitions and inserts a few vectors per partition. Using collection tpart, we add partitions A and B with create partition, which lets us route inserts into smaller logical buckets. The insert calls provide column-oriented data. The first list is prices P, and the second is 2D vectors V, with partition name placing each batch into A or B. Because PK is auto-generated, we only supply P and V, keeping input concise. Call.numEntities returns the total row count across partitions, confirming both inserts landed. The printed result shows total rows, verifying data distribution into A and B. Next, we run a baseline search against the whole collection. This snippet runs a baseline search across the entire collection. We call load to make T-part queryable in memory. Then search over the V field with a simple 2D query vector, Q. The search returns the top 3 nearest vectors without any partition or scalar constraints. And output fields requests the price P for each hit. We take the best hit B from res and print its price, illustrating whole collection behavior. Increasing limit can improve recall, but may cost more latency. Decreasing it reduces work per query. The printed result shows the closest item's price when scanning all partitions. Finally, we combine partition restriction with a scalar expression. This snippet combines partition restriction and a scalar filter in search. We query only partition A by passing partition names equals A, and we apply expr P equal 2.5 so Milvus prunes vectors with higher prices. Together, these constraints reduce the scanned data, keeping latency more stable as the collection grows. We still search on V, but now read far fewer candidates, and output fields returns P for inspected hits. Raising the price threshold or removing the partition expands the search set and can increase latency. Tightening either does the opposite. The printed count confirms how many hits remain after both partition and scalar filtering. In a real system, this maps to tagging vectors by source or shard and keeping a compact numeric summary per vector. Partition by shard or category. Use a scalar like timestamp, price, or quality score to cheaply exclude old or irrelevant items before heavy similarity math. Recap what it is. Partitions split one collection into smaller logical buckets, and scalar filters remove candidates with a cheap numeric test. When to use it. Apply both when you need stable latency as data grows, or when queries often target a subgroup. One caveat: over-partitioning or overly tight filters can hurt recall and routing flexibility. Next step, measure and tune the candidate set size by changing the scalar threshold and the ANN search limit. Then record P95 latency as you grow the dataset. If short, practical IR helps you, subscribe and watch the rest of the IR videos.